Okay, so we'll talk about the modeling process. And this is in general a process that we use to model any types of models, not only predictive models. It's always it's a standard process. And the first thing we need to do is understand the context. Okay, what is the context and that we're working on? What do we want to learn from the data? What are the objectives? If we are developing a predictive model, what are the objectives of that predictive model? Or if we are feeding a time series model, what are the objectives of that time series model? So in general, for any type of modeling process, that will be the approach. What are the expected benefits? Once you're working in a company, you'll see that nobody will pay anything just without getting benefits. So we need to understand what are the expected benefits of a predictive model, of a time series model, of a regression model. What do I expect to win? In fact, when they are very complex projects, you need to do a return on investment analysis to convince management that you have that's a good project to do. Otherwise, management will not invest money just because you're a nice person. How will the results be used? Will the results be used to make very important decisions, or the results will be used just as companions, let's say, to justify some very minor decisions that need to be made? And what is the model selection criteria? So if it is, for example, a time series model, the model selection criteria could be the model that best predicts the next semester of data. Or for a machine learning model, if it's a prediction, if the data is balanced, how we're going to select the best model? Will we use the area under the curve, the area under the ROC curve, or will we use the misclassification rate? Depending on if the data is not unbalanced, we may want to use the misclassification rate. So those are the first things we need to define. Then we need to pre-process the data. We need to prepare the data. So we need to define what we're going to do with missing values. We need to make sure that if we're going to, for example, compare several models, and at least one of those models requires centering and scaling of the data, so that I have a fair comparison, I should center and scale of the data, okay, for comparing all the models. Should I add or remove predictors? Okay, so we need to investigate if we have, for example, predictors that are highly correlated, we need to remove some, or if we need to add a new predictor or develop a predictor based on a transformation of the current predictors that we have. Sometimes it's better to work with ratios of quantities than working with the quantities themselves. During the pre-processing stage, we also split the data in training and validation. So it's always good practice to split the data. We'll talk about criteria to split the data and limitations that we have to split the data depending on the data set size. But for example, even in time series models or regression models, we need to split the data. We need to have to feed the model with a part of the data and then predict the other part of the data. With time series data, the normal thing to do is, if I have, let's say, 5 years of history, and I want to predict 6 months, I would feed the model with the first 4.5 years, and then predict on the 6 months that I already know the answer, to be able to measure how good that model is, computing the root mean square error of the prediction. So we always need to split the data. In the case of classification, and even in the case of regression, it is very important to, particularly in classification, which is cases where we see this thing more often, we need to make sure that if the data is not balanced, and let's say I have a class that in the population only represents 1% of all the cases, a particular type of cancer, maybe 1% of all the cases. Well, I need to make sure when I train the model that the data that I use for training is balanced. And we'll talk about different ways of balancing data. We'll talk about different ways of balancing the data set so that, but we only balance the training data set, not the test data set. If we do not balance and we have a very severe unbalance, it is very likely that we will underestimate that important class, that class of interest, because we have very few observations there. We need to balance. And then we need to always compare models. Okay, the same model is not good for everything. We don't have, there's no such model that is good for absolutely everything that we want to do. We always need to compare models, because even for two, let's say two insurance companies that are trying to predict fraud, two insurance companies trying to predict fraud in the automobile fraud. Well, even though the data may be similar, the model that works better in one insurance company may not be the model that works better in the other insurance company. So we always need to compare different models. Okay, and that happens also with time series models. Time series models, we normally have more than one time series model that fits the data fine, but we need to check forecasts and see and compare the forecast for different models and see which is the model that gives me the largest precision in my forecast. Okay, the same thing happens in regression. In the regression class, it's normally not so much emphasized to separate the data in training and testing, but it's important to do it. And it's also not very often emphasized in regression that when you have the actual data, you need to be able to predict actual data that you already know the answer to, so that you evaluate the model, assess the model. Okay. So we compare models and select the best. Then we tune and validate the final model. We compare several models. For example, in our case, in this class, we'll be comparing, for example, logistic regression with linear discriminant analysis, with support vector machines, and so on. And we need to decide, once we decide which is the best model for our data, then we need to fine tune the model. All the models that we're going to see, most of the models, not all of them, but most of the models that we're going to study here have something called hyperparameters. Hyperparameters are parameters that cannot be estimated from the data itself, but we need to have another device to be able to estimate what are the best values for those hyperparameters. Okay. And then once we fine-tune the model, we use the validation set that we separated from the beginning to be able to see how well that model does in that set that has not been used at all in the training. Okay. And then we put it in production. So we implement and put it in production. Okay. It's also important to establish a periodical validation process. Models change over time. Data is changing over time. So the models will also change. And a model that's very good now may not be very good a year from now. So we normally establish certain periods to validate the model. For example, in the regulators with money laundering models, with anti-money laundering models, regulators require that the models are revised and revalidated at least 6 months, every 6 months, at least two times a year, because we need to make sure that the model keeps being actual, keeps being accurate, and keeps giving the results that we expect from that model. So that's in general the modeling process. And we're now going to focus on pre-processing. And pre-processing, as I mentioned earlier, involves several things. Involves determining what we're going to do with missing values. Are we going to have to impute some missing values? Or are we going to just eliminate observations that have missing values, or eliminate variables or factors that have a very large percentage of missing values? If I have a factor or a variable that has a very large percentage of missing values, that variable is not going to help me in the prediction. In a model that we developed for one sporting club, there was one of the factors that they thought could be very important, and that was customer satisfaction. They call it a partner. They call it partners. A customer satisfaction summary, a survey. But the customer satisfaction survey only had about 10% response. So if you have a variable that has 90% of the data missing, it's better to eliminate that variable. It's not going to help. Okay. The center and scaling, adding or removing predictors is also something we're going to be doing here. Transformations, because we may find that working with a combination of predictors is better than working with the predictor itself. We do the split, or at least we determine how we're going to do the split of the data in training and testing or validation, and we do the balancing of the training data, okay, in the pre-processing stage. So that's what we just mentioned. Now, the stage of pre-processing is critical for the success of the modeling process. If I fail to do a good pre-processing of my data, it's very likely that my model will not be as good as it could be if I do a good job at pre-processing my data. Guys, tell me if you don't hear me fine, please tell me, okay?
Yes, teacher. It is working great right now.
Okay. Yeah, if you stop hearing me or anything, let me know. So pre-process is determined by the type of model. But again, when we're comparing different models, we need to make sure that we're comparing under the same conditions. So even if a model does not need pre-processing, if we're going to compare it with models that need pre-processing somehow, we need to pre-process the model. The models that are not that are very robust against all types of data for training are the decision trees or classification trees. Trees are very robust. They usually do not require pre-processing. They can handle missing values. They can handle very skewed distributions. They can handle all types of data. But other models like support vector machines, like neural networks and so on, they do require some type of processing. Okay. Now we will be focusing on supervised pre-processing. That is, when we do the pre-processing, we will not consider the target variable. The pre-processing applies to the predictors. So we'll analyze the predictors, see if they are highly correlated or not, and so on. We will not consider the target variable in the pre-process stage. So that's why we call it as unsupervised pre-processing. Okay. And another thing that sometimes is very important is the way we code predictors. That is part of what's called feature engineering. So coding of predictors can have a significant effect. Most of the algorithms that we have now available do not do not require a very careful job in coding. Several years ago, you needed to make sure that when you had, for example, a categorical variable, you recoded that variable as dummy variables, okay? And then if you had one variable that had 5 different values, you need 4 dummy variables, and you needed to make sure that the variables were orthogonal and so on. Now the software takes care of that for yourself. So you don't have to do it in general for most of the software packages that we have available. But sometimes using combinations of predictors can be more effective. There is no substitute for subject matter expert. If you're working in a field of chemistry, there is no substitute to having an expert in chemistry, making sure that the predictors make sense, that they doing transformations or not make sense with the predictors, and that will be based on subject matter expertise. As a statistician, one works always with other people, because the statisticians are not experts in everything. So I've worked, for example, with automotive engineers, and that does mean I cannot fix a car. No way. I really will struggle. Okay, changing a tire, I would call the Libra service from Banamex to have them change the tire. Okay, but I work with automotive engineers, and they provided the subject matter knowledge. I did projects in the pharmaceutical industry, so I work with experts in that particular pharmaceuticals that they were producing in that factory, and also work with in financial institutions. Okay, and in different areas in financial institutions. In credit, I have worked long enough in credit and fraud detection that I'm very familiar already with what's going on there. But for example, in finance, in some finance applications, we need to work with somebody who's expert on those things. And for example, the ratio of 2 factors may be better predictor than considering the factors on their own. The most effective form to code the predictors, that is what I was telling you, is to use subject matter expertise. That's the most effective. Okay. We're gonna talk about pre-processing with an example, with a cell segmentation case study. I'm gonna pause here because I'm supposed, in theory, we're supposed to clear the room for a few minutes. Okay. Let's see. Can you guys hear me over there? For is it at home? Or... Can you hear me?
Yes, teacher.
Yeah. Now I hear you too. Okay. Okay, so we're going to look at this case study. It has to do with cell segmentation. This is actual data from a clinical study as it says, for cell segmentation. And what happens is medical researchers try to understand the effects of certain treatments, certain medicines in the size, form, development level, and number of cells in a living organism. That's what they try to do. Now, now, to achieve this, what they do is they examine parts of an organic tissue in a microscope, and they evaluate the cell characteristics. Okay, they try to evaluate the cell characteristics. Now, this is very time consuming and requires that whoever is doing the evaluation is an expert in this type of thing, of cell segmentation. So they require a lot of training, and it's very time consuming because they do it one tissue by one tissue and so on. Another way to measure this, to achieve the same objective, is to measure the characteristics of different tissue samples and utilize something that they know, these researchers know as high content screening or high content detection. That's a method that they use. So I tell you, this is an actual method that is used by medical researchers. Now, a sample is first dyed with a substance. Please let me know if you hear me okay, especially those of you in your house. Samples first dyed with a substance that will bind to the desired characteristic of the cell. Then they apply a stain, type of stain, to the sample that attaches to the cell's DNA. So this stain that they apply attaches to the samples, to the cell's DNA. Then they interrogate the cell by an instrument, in particular they use a monofocal microscope, where the dye reflects light, and the reflected, that light that's reflected takes a quantity, quantify the degree of staining for that specific wavelength. So that microscope has different wavelengths, and then they send a signal, and they read the response of that signal, and that response is telling them the degree of scattering for that specific wavelength. And if multiple characteristics of the cell are desired, then multiple lights and multiple light frequencies can be used simultaneously. So this microscope can emit different lights at different frequencies and detect back the reading those lights of different channels. So different lights represent different channels. Then this is a research that was published by Hill in our authors, 2007. Here's the reference. We utilize this high content detection to measure several aspects of cells and observe that software utilized to determine their placement and form with a lot of difficulty segmenting the cells. But the software was not working the way they expected the software to work. Now, for this research, the guys who wrote this paper assembled a set of 2019 cells. 1,300 were classified as having poor segmentation, PS, that will refer that to PS, poor segmentation. And 719 were well segmented, that's WS, or well segmented. 1,009 were reserved for the training set. So they separated 1,009 just to train the model, train a model. And if you see this picture here, you see, for example, this cell here, B, the one that you see here in B, which is this one here, would be a well-segmented cell, but this one would not be a well-segmented cell. Okay, that's E. So that's this one over here. This is poor segmented. It's here. The red boxes show poorly segmented cells, while the cells in the blue boxes are examples of proper segmentation. These are the blue boxes. This is proper segmentation, and this is bad segmentation. Now, poor segmentation in both of these, the D and E, poor segmentation. So, as you can see, you can do this thing by viewing looking at the microscope and trying to classify a cell as well segmented or not well segmented. And that would be very, very time consuming. Now, for a particular type of cell, they utilize different stains that would be visible to different optical channels. Channel 1 was associated with the body of the cell and can be used to determine cell perimeter area and other qualities. That's channel 1. In channel 2, let me see if I go from here. Channel 2 interrogated the cell nucleus by scanning the nuclear DNA. Channels 3 and 4 were said to detect these two substances, one's called actin and the other was tubulin. Don't ask me what they are. Okay? I don't have an idea. These are two types of filaments and are part of the cell's cytoskeleton. For all cells, 116 features, which are, for example, cell area, spot fiber count, and so on, were measured and were used to predict the segmentation quality of the cells. So we have 116 features. So 116 predictors to be able to segment the cells. Was particularly useful for some in some models that we're going to be using. So we're going to do it here because we're going to compare eventually several different models. We may not do all the model comparison using this data set because it's very large, and some of the models will require at least 32 gigas in RAM in your equipment, and that so you will be able to. If you have less than 32 gigas in RAM, you could not process some of the models. Okay. So we will not work with the whole set. We did transformations to reduce bias. We'll see now the data, and you will see that some of the predictors have very skewed distributions. So we need to reduce bias because some models are very sensitive to that. If we have very high bias, that means we're very far away from normality in the continuous predictors. That's not good for several models. Okay. For example, one of the predictors is the standard deviation of pixel intensity in the active filaments. And this is the distribution. This is a histogram of the standard deviation. So as you can see, it's a skewed distribution. It can never be less than 0, it's the standard deviation of a particular variable, and it's a skewed distribution. So when the distributions are very skewed, it's a good practice to remove that skewness. And we'll see, we're going to do that through a transformation to reduce that skewness. What we're going to be using is the box-box transformation. Have you seen that box-box transformation you've seen it in regression? Sure or no? We use the box-box transformation. The box-box transformation has the advantage that it helps achieve symmetry, to approximate normality. So that skewness is going to be reduced with this transformation. In this example, we'll see 69 predictors were not transformed, since some of them contain 0 or negative values, and then you cannot apply the law. So remember box-box transformation when there's a parameter lambda, that is the one that's chosen to approximate normality, and if lambda is equal to 0, that's equivalent to taking the logarithm. And the log, we cannot take the log of 0 negative values or zeros, so that's 69 were not predictors, that were not transformed. And 3 predictors have a lambda estimate very close to 1, so we're not transformed either. Now, as you can see, with so many predictors, doing this thing one by one will be very time consuming. Trying to look at the distribution compute the Box-Close transformation, and then check if lambda is close to 1, then do not do the transformation, so on. But we'll see that we can do automatically with CAD package. That's the Box-Close transformation. So it's x to the lambda minus 1 divided by lambda. If lambda is different from 0, and log of x if lambda is equal to 0. Now I'm going to go to R. I'm going to switch to R now. Okay, so I was saying the data set has 119 variables, and the first, when we looked at the case variable, get case, I have a classification there. I have a label that identifies either the testing or the training data set. Okay? Now I'm gonna, if you look at the structure of segmentation original, most of the variables are numerical. Okay? I have some integer variables, but most of them are numerical variables. And the first one, so let me look at here. Case is a factor because with 2 levels, which is test or train, and then the class is the response. Okay, it's a response. Remember, it's poor segmentation or well segmented, poorly segmented or well segmented. So it's PS or WS, well segmented and poorly segmented. They are coded as 1 and 2, although the original data comes coded as 0 and 1. 0 and 1, the 1 is the one well segmented cells. So those are the cells of interest, the ones that are well segmented, and we want to predict based on those and the 100 and some variables, 100 and some predictors, if a cell is going to be well segmented or not. Okay? Now, the dimension, we already know the dimension is the same, is 2019 by 119 columns. Remember that of those 2019, about 1,000 and some were test training cases. Okay. Now let's look at the proportion of well segmented. Here's the case. The proportion of cases we have 50% for testing and 50% for training. Roughly 50% for training. And we're going to create now the training set, the segmentation that I'm calling it seg train. I'm going to have all the observations that correspond to the training set in this subset, okay, in this data frame. And we have 1,009 rows with 1,009 cells with 119 variables. Now, the first 3 columns, we don't need for prediction. We need the class because that's the response, right? But remember, the first 3 variables were they, I have them here. Cell ID, the case, whether it's trace, test, or train, and the class. The class which is the response. Now, we're going to eliminate the first 3 columns. Well, we need to keep the class column as a response. We need to keep that response, of course, because that's what we're going to use to create the model, to train the model. Okay? So I'm going to say seg train class. I'm going to set that variable apart. I'm calling it seg train class. And I'm going to put the class variable there. So seg train class is a response. Seg train class is a response. And that's all I needed because I already separated my training for testing. So now I just have to remove the third column, which is the first three columns. In the case the cell ID, I don't need that. The second, it's just I already took the training data. And for the third column, I already separated the values of that third column in sec_train class. Okay? Just for sec_train, for the training data. So I only have 1,009 observations, 116 predicted variables, and because the response is already in sec_train class. So 116 predictors. Now, the original data, and that comes in the paper that you have a reference for there, contain several columns that are called status. And these columns are binary versions of the predictors. So since they are duplicating the values of some predictors, we need to remove them. They're essentially duplicating the information. So that we need to remove them, all the variables that contain the string status. And to do that, we use the function grep. Remember, the function grep is useful to select certain string of characters, and I'm gonna call a status call number. I'm gonna say which call numbers essentially I'm gonna have here have the string status in the names. See, so it's gonna take the names of sec_train X, and of those names, it's gonna tell me which columns have the string status in the name, because I need to separate those. As you can see, the sec status called none only has a bunch of numbers which correspond to the column numbers of the variables that have the word string status in the name. Okay. Now I need to remove them because they originally have, this is my dimension, I have 16 variables. Once I remove all the variables with status in their name, which are, so I take sec_train X and all the rows, that's why this comma here, and then I'm removing the numbers, the column numbers that correspond to this vector of column numbers that have a status in their name. Do that. And now I'm sorry, repeating the same thing. I didn't remove them yet. I'm removing them there. And now the dimension has reduced to 58. So now I have 58 predictors. Okay? 58 predictors, because I removed predictors that were duplicating information that I already have in the other variables. And those are the predictors we're going to start working with. And this here is just the first few data points there. If I want to see what they have, those are the first 6 observations in the segmentation original set, and these of course will not have the test set. And this will have only this has all the variables, all the test and the training set. Now, let's look at the transformations. Remember, we mentioned that some of the variables represent the standard deviation of other variables. So those variables are expected to have a skewed distribution. For example, let's take one of the variables, which is var channel 3 intensity in channel 3. This is the column that corresponds to the variance, okay, of the standard deviation. It's called var, the variable, but it contains the standard deviation. So let's look at that. If you look at the maximum of that variable is 870, And if I were to divide it by the minimum, sorry, the maximum divided by the minimum is 870. So that is showing a very high level of skewness, right? We take the highest divided by the smallest one, and we get something greater than 10. We have a high level of skewness, and that's confirmed by measuring the skewness. I can compute the skewness of this variable, and the skewness is 2.39, which is much greater than the skewness of normal distribution. And the histogram confirms that. That's the histogram that you already saw in the slide presentation. Okay. So one thing that we could do then is transform those variables that are skewed to make them less skewed, make them more symmetric. Okay. Now, to do this thing for all the variables that are numeric, we can use this function, which is an apply function, to calculate the skewness in columns, and that will, we just say apply, and then the function we need to apply to the columns. Apply works is the data frame, and then the margin is 1, applies the function to the rows, and 2 applies the function to the columns. And which function? This function. This function could be anything, could be the maximum, the minimum, could be the standard deviation, the mean, whatever. So I'm gonna compute the skewness of all the columns in set train X. So the function is skewness applied to the predictors in the training set to all the columns. And I have skewness. If I look at the head of this, I have the skewness for these variables. Okay, all this is very small, but this is very large skewness, 3.52, 2.95, and so on. Okay, now which variables correspond to those values of skewness? These are the variables that I just listed the first 6, okay, here. That's why I said head. Remember, head lists the first 6 values and tail the last 6 values. I can change that to the first 10 values or the last 10 values, whatever. So these are the variables that for which the function skewness was applied to. Now, we can utilize all these values to prioritize the variables and see which of those we transform. Okay? Now, the function we're going to use, the box-box function from the mass package. This is a box-box transformation. We'll use that from the mass package. There are other packages that have box-box transformations. When you're doing time series analysis, for example, the box-box transformation that is used is different than the one we're going to use here. This box-box tries to achieve normality or symmetry, okay? Whereas in time series, what you want to do is achieve constant variance in time. So the algorithm changes a little bit. Now we will use the function box-box to estimate the value of lambda. So let's do it for one variable only. So I'm going to do it for this variable that we start analyzing here. I'm going to say var intents ch3 and then trans because it's transformed. And I'm going to say take box-box transformation of the same variable. Okay? Like that. And now I look at var intents channel 3 and tells me what it did. This structure has the information on what transformation it did. It tells me here that the largest to the smallest ratio was 871, the skewness was that, and the estimated lambda was 0.1. So with fudge factor that is approximating that they compute the mass function for Box-Cox transformation computes a confidence interval based on the normal distribution and on the maximum altitude, because lambda is determined by maximum altitude in this transformation, this Box-Cox transformation. And since 0 is in the confidence interval for lambda, for the optimal lambda, which was 0.1, it chooses 0, it chooses the log. Okay, it chooses automatically 0, which is the log. So it says here lambda is 0 will be used for the transformation. Then after the transformation, I look at variant 3.tr. How do I apply the transformation? I computed the transformation here. See, I'm saying compute the transformation as the Box-Cox transformation of this variable. Now, to apply that transformation to the variable, I can use the function predict. Because what this structure has all the information to make that transformation. So I can use the function predict to apply the transformation that I computed here to the original variable. So I say variant 3 tr, transform, as predict the variable, the function to transform the variable to the original variable var intent channel 3. Okay. And var intent tr now has a transformed variable. Now let's look at the first few values. Let me see head here, and I'm going to say here just the first 6 values, first 10 values. And the first 10 values of the transformed data, of the original data, So these are the logs of these values here. It took the logs. So I already applied the transformation. Now I can measure the skewness of the transformed variable. Okay. Say skewness, and now skewness is minus 0.4. It's very reasonable, and the histogram looks symmetric. Okay, the histogram looks symmetric, so we've corrected the skewness in that variable. Now, we could do the same variable by variable. Okay, we could do this for each one of the continuous variables that we have. Instead of doing that, there's a function from Kaggle that's called preprocess. This function will do a lot of the pre-processing for us. And one of the things that the pre-process function can do is can apply the Box-Cox transformation. And so to apply this thing to all my variables, my predictors, all I have to do is I'm going to say seg pp, or preprocess. I'm going to pre-process my predictors with the function preprocess. I'm going to take the predictors from the training set, okay? And I'm going to say that the method for pre-processing is going to be Box-Cox. SegPP preprocess, I'm going to preprocess the predictors, and I'm going to use the method Box-Cox. Now, compute SegPP. The SegPP has if I look at the names of SegPP, has all this information, has the BC, has a bunch of values that we will not look at now because we did not do it. But the only thing we applied was Box-Cox. Okay, that's the only pre-processing we did. We will see later that in the pre-process function, we can do other things. We can impute missing values. We can center and scale data. We can, for example, in terms of imputing missing values, we can use different methods. We can use k-nearest neighbors and other methods to impute missing values. Here, all I did was a box transformation. So that's the only one that's going to have some information. It tells me here the box, when I look at the names of segpp, which is the preprocess, the function, the variable, the element BC of this preprocess, it has the variables that preprocessed using the box transformation. Okay? So that it does have that. If I look at the structure, let me look at the structure here of segpp. See, this is a very neat function because it tells me it did not do a lot of things that it can do, but let's look at the box transformation. I lost it, I had seen it, now I lost it. Example, let's look at this one. This one is, let's look at the channel. We have been working with channel 3, intensity channel 3, right? Let me see if I find it. Okay. This is the one that we have been looking at, average intensity channel 1 or channel 3, whatever, doesn't matter. We, this variable, it tells me what it did with this variable. For this variable, it found an optimal lambda of minus 0.3 with a fudge factor of 0.2, and was used with this one here, and the lambda that it used then was minus 0.3. We don't, this did not cover the interval, the complex interval did not cover 0, so it did not take the log. Let's look at another one. To another variable. Diff intensity. See? Diff intensity. Here the lambda was minus 0.9. The fudge factor was 0.2. So if you add and subtract 0.2 to this, it didn't transform the variable. So this variable left it untransformed because lambda equal to 1 was in the confidence interval for the optimal lambda. So it will only transform those variables that needs to be transformed. It will not transform those who don't need to be transformed. So it's a very neat function that saves us a lot of work, particularly when we have many predictors. You have 5, 6 predictors, you can do it one by one, it doesn't matter. But if we have 50 some predictors or whatever, that's very useful. 58 predictors in this case. So to apply that, the preprocessing, to apply the transformations where we have to apply them, all we do is use the predict again. Okay? So let's look at I already did the preprocessing here. I'm doing the histogram of some of the variables. We already seen that. Okay, that's the original intent channel 3, and this is the transformed variable with the log, and this is the perim channel 1, and that's the histogram, which is also skewed, and this is the transformed perim data with the seg train trans with the transformation. Okay, so the preprocess will help us do the box transformation to a bunch of variables, very easy, and it will only apply the transformation where it needs to apply it. And if the value of lambda is very close to 0, we'll take the log. Okay, it will always round to some, if that number is in the confidence interval, we'll take some reasonable number. For example, if I got an optimal lambda 0.4, it will close it with the fudge factor, we'll do a 0.5, so a square root. Okay, so we'll try to get to reasonable numbers. So now let me go back to the presentation. And Okay. That's where we left here to go to R. That's where we went to R. Now, let's go look at all transformations that can also be done with the preprocess function. Now, this is a transformation that should only be done if absolutely necessary, okay? Because one has to be very careful with when one does this transformation. This is for outliers, for treatment of outliers. When we have outliers, and we have a model that's not robust, if we have a model that's robust against outliers, we don't have to worry much. Like all decision trees, all classification trees are robust to outliers. But support vector machines, they are not robust. They ignore part of the data set when the data set has outlier. So when we train the model, if we have outliers and we haven't dealt with them before, so algorithms like support vector machine will eliminate them, will essentially ignore some observations. Maybe that's what we need to do, but we need that has to be our decision and not the solver decision. So if the model is sensitive to outliers, then there's a transformation called the spatial sign transformation. And that transformation is very useful because it projects all the predictors into a unit sphere. Okay, if we have two predictors, it will project them into a unit circle. If we have three predictors into a three-dimensional sphere, unit sphere, and so on. Okay. Transformation takes the original value and divides it by the square root of the squares of each of the variables, of the p variables that we have. Okay, that's what the transformation does. It transforms and projects everything to a circle. And if you look at this denominator, it measures the distance to the center of the predictor's distribution. We'll see the model center at 0, so that's the distance from the origin. And if we use this transformation, it is important to center and scale predictors before we do it. And before we do the transformation, we need to center and scale the predictors. Okay? Because I forgot to put my. And I'm recording this thing is when. Okay? Essentially, what it does is this. You have this data set, these are outliers, right? Both the mass of the data is centered in this area, and we have these observations which are very far away from the rest. Once we apply the sign transformation, these values are projected to the circle. Now, what I'm saying is that they don't see what I'm pointing in there. If I draw now, let me see if I draw things here. No, you don't see that, right? I'll figure out later what I have to do to make that happen. See what's happening here. Okay. I'm going to use the icon here. So this data point, for example, may be this one here. Okay. So now all of them are the same distance from their origin, and what look like outliers here don't look like an outlier. It doesn't show there either. Okay. Let me see. I think I know what happened. When my computer went down, my iPhone, my iPad was cleared as the host, and the other. Okay. Now let me see if I draw here. No, it's not working. No. Did you guys see me when I point at the blackboard in your homes? Yeah? Oh, okay. It's just the drawing that doesn't show, right? Okay. Now that's another type of pre-processing. Now, when we do that, we need to be very careful because first, if we like to scale the data, we have to do the scaling before we apply that transformation. And then when we predict new data, we need to keep track of the transformation that we did to do the same transformations to the data that we're going to be predicting. Okay? We have to be careful to remember which transformations we apply to the pre-processed data. Now, there is an easy way to do that. When we talk about the train function, we'll see that the pre-processing can be done with the training in the train function. And that has the advantage that the train function will remember exactly what you did. Okay? Okay. Now, another thing that sometimes done is to apply principal component analysis before we do classification. That used to be necessary when we have too many variables and we needed to reduce the set of variables so that we could compute our model in our computers. Okay? Now, it's unless you have hundreds and hundreds of predictors and millions of observations, that will not be necessary. But that's a tool that has been used, okay, to reduce the dimensionality of the predictor space and have a more remote management. The disadvantage is that when we do principal component analysis, that's not taking into consideration the response. And the projections that we do in PCA may have nothing to do with the classification we're trying to achieve. For example, in this particular case, that's fully segmented, they're well-segmented cells, and those are the transformed with the principal components and the second principal component 1 and 2. So we may seem to see here that there may be some better separation with the principal components. It's not that clear that that's happening. Okay? So, but sometimes it's useful to do it. And although I would only do it if it's strictly necessary to reduce dimension before we apply or we determine a model to do prediction. The principal components can result in meaningless combinations because they don't take into consideration the response. So it can really result in combinations that are meaningless, that do not have anything to do with the problem at hand. And as we saw earlier, at the beginning of the semester, before performing PCA, we need to center and scale the data. That needs to be centered and scaled. And that's just what I said. The main issue with PCA is that it ignores the target variable. Does ignore the target variable. Okay? Now, after correcting for bias, once with the data that after correcting for bias, we apply the Box-Cox transformation. After we do that, the first four principal components represent 42% of the variability. So that's still very low. That's still very low percentage of variability. And it would be wise to use only those four principal components to try to do classification. That's with the principal component 1 versus principal component 2 and 3. And we can see how the data looks when we plot the well-segmented cells and the poorly segmented cells with where each of the principal components pairs. Now, when we looked at PCA, we saw that it's sometimes used as a descriptive tool to try to associate if some predictors fall with the principal component 1 or principal component 2. For example, which predictors have more loads into principal component 1, to see if there's something common to those predictors. That's why we looked at the loadings of the variables in the principal components. So that can be done. Let me look at the graph here. Okay. For example, here, if you look, this is the scatter plot, and that's channel 1 cell body. This is the red. Okay, the red are the channel 1 cell body. Then the channel 2 is the blue, channel 3 is the green, and channel 4 is the black. You can see, for example, that this is principal component 1. When you look at principal component 1, it's 1, 2, and 3. The same sequence that we have there. PC1, 2, and 3. PC1 versus PC2. You know, the graph. And you can see, for example, that channel 1 is more, the variable that seems to load more in channel 1 is the cell body. Okay? It's the cell body. And channel 2 would be the nucleus, and channel 3 with the actin, channel 4 we actually you see channel 4 here will be tubulin. But that's information that it's only relevant if the subject matter expert says it's relevant. Otherwise it doesn't add any value. Now, treatment of missing values. Missing values, we have talked about missing values before, and we've seen that with missing values, first thing we need to understand why they are missing. Because there's informative and non-informative missing values. For example, when you took statistical methods and talk about sampling surveys and all that, some of the questions have a lot of missing values. Well, that has some meaning. If you ask somebody their income, there's very often missing values in that response. Or if you ask somebody their age, okay? People don't want to answer their age, for example. So there's some that's informative missing values. You need to rephrase the questions so that people are free to answer those things. We need to understand if the missing values pattern is related to the result, okay? That's responses for example, responses from a patient to a drug or treatment. you have missing values. Here it's important to distinguish missing values from censoring data, censored data. Have you heard of censored data? No? When you do a clinical study, you follow the patients for a certain period of time. So you apply a treatment and you try to see if the treatment works, but you cannot go forever. So you say, well, I'm gonna follow on these patients for about a year. After the year, if they have survived, or if they have not, or they have not been healed or whatever, then they leave out, they are out of the study. But you don't know if the treatment worked or not. They don't know. They could die the next day after they left the study. That will be censored because you need to end at some point in time. That's not a missing value. A missing value is when a patient withdraws from the study and says, I don't want to participate anymore. That'll be a missing value. That's not censoring. Yeah. Customer satisfaction evaluations are sometimes missing values have a pattern there. Normally, if you are very unsatisfied with something, you complain. Okay, and you want to reflect that in when they send you a survey. Are you happy with the service? No, I'm not happy. But if you're happy or it's okay with you feel lazy, don't answer the survey. So missing values are normally associated with people who are sort of okay. They are not excited about your services, but they are okay. And I discussed this in censoring. That's very important. For example, in manufacturing, missing censoring also occurs. It occurs in clinical trials. It occurs also in manufacturing when you test something for resistance. For example, if you look at these like very thick springs that go with the trucks in the muelle, I don't know how, I forgot the name for muelle in English, but anyway, they are tested for resistance. So what they do is they subject these springs to pressure repeatedly, and sometimes they have a machine that is pressing thousands and thousands of times. And the test may call for 10,000 tests, okay? But maybe if the spring breaks before that, that's okay. That's a useful observation because that means that it don't resist the test. Now, if it doesn't break, that's censoring because you don't know if you have kept it for 100 more pressures, then it would have failed. So you don't know. That will be censoring. That also happens there. In clinical trials, that's where it's most common to happen. And the missing values are more often related to the predictors than to the sample. If for certain predictor the percentage of missing values is very large, it may be preferable to ignore it. Okay? If I'm 90% of values missing, then it doesn't make sense in considering that predictor. And decision trees algorithms are not impacted by missing values. So that's one of the advantages of decision trees. And a possible solution for models which are sensitive to missing values is to use imputation. And imputation can be done in different ways. One common way to do imputation is to use a certain observation is missing. You look at the responses for all the other variables, okay, and look at the nearest neighbors, and then use the nearest neighbor's information to impute the value for that missing value. Okay. So you can do that approach, take the average of the 10 nearest neighbors, or you could do instead of the average, you could take the median of the 5 missing values, the nearest neighbors, and so on. Okay, so